Okay, first is an announcement about the test. I have not graded the test yet. I finished the first page and that's all. And I didn't have any guilt over not having it done for you today. So I will have it back on Friday. I'll give it back on Friday. I have projects that I will give you. Yeah, I'll give you the projects back today. Okay, so here's an announcement for the sample problems heading into test 2 a few weeks from now. You're not responsible for 65B, so make a note of that someplace. There's a problem in that sample packet of problems that Caitlin and I have decided we're just not going to cover anymore. So 65B you don't need to worry about. All right, so speaking of Caitlin, Caitlin was in charge of this new packet, packet 2. So any mistake in packet 1 was me. Any mistake in packet 2 is Caitlin. So I'm going to be pointing the blame. Yep. Yeah, this is not me. Packet 3, it's mixed, but I'm not going to tell you which ones are mine. All right, so today we cover 2 new integration techniques. These are largely our last 2 integration techniques, partial fractions and trig substitution. So I'll say that these are really, really out there, and after we've finished with them, you'll have a good sense of the great lengths to which people needed to go to find antiderivatives before we had tables and before we had Wolfram Alpha. Was these really crazy, crazy techniques that we're going to see today. But like I said, they're kind of, like it's just outdated. You can type just about anything you want into the computer. All right, according to the calendar, your grading choice is due on Friday, but that was assuming I handed you the test back today. So I'll hand you the test on Friday, and then on Monday you're going to tell me how you want me to grade you at the end of the semester, okay? All the details are in the syllabus. You can take a look. All right, so, and there's no projects at the moment, so let's jump in on the new packet. So the first page is a reference sheet, which you will bring with you to quizzes and tests. We jump to page 3. You can continue to use that other reference sheet on quizzes and tests. All right, so I think that's it. All right, everybody has a packet, right? Okay, daily summary. Stefan, you're not on page 3. Haley, daily summary. How exciting! You weren't excited about that? So so you don't need to pull your table out, but here's a table that we've looked at. So so take a look at formula 26. You guys remember we used 26 and 27 back on our table day? And these LNs kind of appear out of no place. And I mean, there's stuff in the bottom, but why? Why are there LNs? So today we're going to figure out where that formula came from. And then down here, number 28. This 1 over a squared minus x squared. So arc sine I can buy. I don't know if you have that one memorized, but the arc sine came from 1 over the square root of 1 minus x squared. So it's basically that formula. But then somehow when it becomes an a instead of a 1, it becomes x over a. And we'll talk about why that happens today too. Okay, so let's start with number 1, this new integral, 5x minus 10 over x squared minus 3x plus 4. So you're going to follow along with me here as I try to convince you that we can take that integrand and rewrite it. First, we're going to factor that bottom. So what does the bottom factor as? Minus 4 plus 1. Okay, so we factor the bottom. And now I'm going to try to convince you that we can figure out how to rewrite that fraction as the sum of 2 other fractions. These 2 fractions where a and b are constants to be determined. So copy that down and then I'll convince you that it's reasonable we could be able to expect that we could find a and b to make this true. Oh. A and b are constants. These are going to be constants. Oh. Okay, so let's see if we believe that it's reasonable that we could find a and b to make this true. If I just gave you the right-hand side and I said add these 2 fractions, what would you first have to build? Common denominator. And what's the common denominator for these 2 fractions? yeah, it's the original denominator, right? It's x minus 4 times x plus 1. So there's some kind of like a cross thing here, right? Like the a would need an x plus 1 next to it, and the b would end up with an x minus 4 next to it, yeah? And so if we pick a and b just so, then maybe we can get it so that when we smush all that stuff together up on top, we get exactly the thing we want, 5x minus 10, okay? So on the one hand, it kind of looks like it's out of left field, but it seems reasonable. If we just added the things on the right, we could probably build just about any linear thing on the left. So this is what we're going to do. And the first thing we're going to do is get rid of all of these denominators by multiplying both sides of this equation by all of those denominators. So everything times x minus 4 and x plus 1. You already don't like it. I warned you weren't going to like it. Okay, so massive distributing here. All of this is coming in to the left-hand side and to the right-hand side. So it's actually going to hit all three of our terms. And it's going to cancel lots of stuff out. So on the left-hand side, what do we have when this entire blue thing comes in? It's just the 5x minus 10, right? Entire denominator gets canceled. And then the a over x minus 4, which part of that blue thing is going to cancel? Is the x minus 4, and so we'll still have next to the a the x plus 1. So it's a times x plus 1 plus b. You're really waffling, Rich. B times x minus 4. See that? A and b are constants that we're going to figure out in order to make it so that we get 5x minus 10. Okay, everybody all right with that next line? Sure looks a lot better than the previous line. Okay, all we have to do is figure out a and b to make this equation true. Now there's two techniques. I'm going to show you one. The one I'm not going to show you is distributing. You could distribute the a, you could distribute the b, and then make these two guys match up perfectly. Like the thing in front of the x over here is a 5. There's going to be some stuff in front of the x over here, and 5 better equal whatever is in front of the x. My preference is to pick good values of x. So for example, if I pick x equals -1, then that term next to the a will completely vanish, yes? And so we're just going to plug x equals -1 everywhere, and we'll have an easy equation with b in it. So how much is the left-hand side when x is -1? -15 equals a times how much is in here? 0, that's the idea, plus b times how much is in there? -5. Right? That equation is supposed to be true for every x. So I'm just going to pick an x that makes it easy for me to solve. So the a part disappears. How much is b? B is equal to 3, yeah? With your neighbors, pick a value of x to go back into that black equation that's going to make the b part drop out. There's one value of x I want you to pick, plug it in every place, and solve the resulting equation for a. Check in with each other on this one. Okay, I heard some groups say a equals 2, is that right? Okay, so I will say that none of what we have done so far involves calculus, right? No derivatives, no antiderivatives. This is a pure algebraic technique. So let's get back to the calculus part. The original integral, we'll squeeze it in down here, is equal to, so what we've just discovered is that it's equal to a over x minus 4 plus b over x plus 1, where a and b are the numbers we just found. So I'm just going to plug them in. 2 over x minus 4 plus b over x plus 1, what does that become? 3 over x plus 1. Parentheses around the whole thing now and a dx at the end. Everybody see what we did there? Just go back to your original equation and plug in the a and b that we just found. And the hope is that those are two easy integrals now, right? There's a plus sign between, so mentally I'm separating it into two integrals. And the integral of 2 over x minus 4, it's a u substitution. We're not going to do all the details, but what is u? Is x minus 4, and basically this becomes a 1 over u. There's a 2 that in my mind is out in the front now, and so there's an ln, right? It's just ln of u. So the 2 comes out, ln of the u was x minus 4. And then the same idea on the other guy. 3 comes out, ln of x plus 1. So just highlighting here, this is a u sub. It's okay if you need to take more time on the u subs than we just did. It's on the sheet, right? And so we can now reference that table that we used before. Let's see, where is it? Okay, so then what we ended up with, let's see, we had x minus a, no, it was this cx plus d business, right? X minus a, x minus b. Okay, we ended up with a 1 over a minus b and then an ac plus d. I don't know what's going on. There's a lot of numbers and letters flying around here. But if you crunch through all of that stuff, you will end up with 2. You can try it later. ln of the one guy and then ln of the other guy. So the table kind of is starting to make sense. ln of one guy and ln of the other guy, and still not quite see how bc plus d and then a minus b is part of it, but apparently if you do this technique, you'll end up with that formula in general. Okay, so that technique is called partial fractions. And the one that we just did there involved factoring a quadratic, right? X squared minus 3x minus 4 we factored. So depending on how that denominator looks, that dictates the way that you set the formula up. Like I set it up as an a over x minus 4 and b over x plus 1. So depending on how that original denominator looks, that's going to change how the setup is. So here's the rule. It's in the table. If you have a factor in the denominator of x minus c, then you just put a number over x minus c. We had 2 of those guys just added up, right? Those are our 2 fractions. But if it happens that you have a repeated factor, like x minus a number squared or cubed or to the 4th, then you put a number over the thing originally, and then another number over the thing squared, and another number over the thing cubed, all the way up until whatever that highest power is. So yeah, factor for each one. So let's start looking at this example down here. So x minus 1 is just a single linear thing. So it gets a single letter on top, a over x minus 1, that one's done, okay? But the next guy, x plus 1, is squared. And so the rule that we just saw says, okay, you put x plus 1 with a letter on top, but also you put x plus 1 squared with a letter on top. And if it had been cubed, we'd have another guy out here cubed. See it? So that's repeated linear factors. And then finally, if you have a quadratic that is irreducible, that is to say that you cannot factor it, then instead of putting just a straight constant up on the top, you got to put a generic linear term, an ax plus a b. That's the only thing that gives you x's on the top. So this x squared plus 4, can you factor it? We can't. And so that x squared plus 4 doesn't just get a single constant letter on top, it actually has a linear thing with an x in it. You see that? Okay, so you don't need to memorize all this because that is all on the reference sheet that you're going to bring with you to tests and quizzes, but you got to be able to use it. So let's see if we can set up, that's fine there. Okay, moving on to 3. You'll have a chance to practice setting up more complicated ones in the activity. So in number 3, it says, why shouldn't we try partial fractions on these? Okay, the first guy, what are we supposed to do with this? If you just let u equal the bottom, like just a normal u substitution, then what is the derivative? 2x plus 2, which is exactly the top. So there's no need, like I don't want every fraction that you see to all of a sudden become, hey, partial fractions is the first technique to try. That's not the case. U substitutions is still the first technique to try, right? So if you get lucky, great. We're not doing any partial fractions. It's just a straight U substitution. In part B, can you factor this guy? X squared plus 1. No, okay, so irreducible was our fancy word. So you can't factor. And if it's irreducible, if it's an irreducible quadratic, then you remember we were going to end up with something like ax plus b on top of that irreducible quadratic. That's what we just saw on the table. And that's exactly what we have. So you can do the work if you want to, but you're going to get that a is 2 and that b is -1, and you'll just get right back to where you started. So it doesn't make sense as a standalone denominator to try this. You're not going to get any place. Okay, so moving on to 4. If you thought partial fractions were bad, you haven't seen anything yet. So let's try trig substitution. And we're going to try number 5 here, actually. 1 over the square root of 9 minus x squared. Okay, my first reaction is to try u substitution. Don't write it down because it's not going to work. But what's the natural choice for u? 9 minus x squared. And the problem is that there's no x like floating around somewhere for us to play with, right? So we tried it, didn't work. So we need a new technique. Okay, so we are going to do a substitution here, but it's going to be a really strange looking substitution. So so just stay with me here as I do a very strange thing. I'm going to let x equal 3 sine theta. That's my substitution. Okay, so you could call it u if you want to, but it turns out it's convenient to think of this guy as an angle, so I'm calling it theta. But also when we do use substitutions, what we would usually start with is u equals, right, something. And here I'm starting x equals and my u is buried inside. That's the theta. But just follow me for this for a little bit on this one. So once we have our substitution, we take a derivative. So the derivative is 3 cosine theta times d theta, right? That's our derivative. Okay. So going back to the original integral, let's just start substituting parts. Downstairs, square root of 9 minus, what do we have that's squared? 3 sine of theta. You'll see why. So that's the x. So we could just change it to 3 sine of theta. And I see a 1 on the top, and I also see a dx. So what do we put there? It's 3 cosine theta d theta. Does everybody see the different pieces? It's not clear that this is any better. In fact, it looks worse to me. But at least it's equal, right? We haven't broken any laws or anything. I'll also highlight that it's very easy to just say, oh, dx becomes d theta. So first of all, it's not true, right? I mean, dx in this case was 3 times cosine of theta d theta. But even more than being not true, if you just forget that you're supposed to like take this derivative in here and you just put d theta, oftentimes you'll take an integral that we're supposed to be able to do, like we're going to be able to do this in a second, and you'll turn it into one that's impossible. And so there's a very steep penalty for forgetting that you're supposed to take a derivative and actually replace equal things with equal things. Now this is right here, but what I've seen is that sometimes students forget that they're actually supposed to take this derivative, this dx equals, and calculate the derivative of sine. And then just put a d theta there, not really understanding we're trying to substitute equals for equals, and then make the problem impossible. Okay, so let's keep crunching through here. This is equal to, I'll put the 3 cosine theta, you know what, I'll put the 3 outside. Cosine theta is still here. But the bottom is where the magic is going to happen. So this is equal to the square root of 9 minus, so squaring everything in there gives me 9 sine squared. Yeah? So that's just the 3 times sine of theta times 3 sine of theta. What can we factor out in the bottom? There's a 9. Okay, let's do that. Equals, there's a 3 in the front, copying cosine theta d theta. 9 here, and then what's left? 1 minus sine squared theta. And there's the trig identity there. 1 minus sine squared is really equal to cosine squared, right? Right, because sine squared plus cosine squared is 1, so So this equals 3 integral cosine theta d theta over square root of 9. And then we said that's really just cosine squared. And then good things. Yeah, there's really only two that you'll need, and one of them is the one we're just using here. So sine squared theta plus cosine squared theta is the one that we just used. And then the square root of 9 is nice, that's just 3. And the square root of cosine squared is nice, that's just cosine. And I said the magic was down there, and maybe this gets at Alex's question from before. Why did we choose this random 3 sine of theta so that this would work? So that you'd end up with a 1 minus sine squared, which you could change to cosine squared, which comes out as cosine. So all of that work gets rid of the radical, right? The original problem had a 9 minus x squared inside of a radical. Being inside of a radical is really problematic for us integral-wise. We just got rid of that radical. That's right. So that 9 is where we got the 3 sine of theta, so that when it got squared, it would become the 9. Okay, here we go. Integral cosine theta d theta is upstairs. Downstairs, we said the 9 comes out as a 3. Cosine squared comes out as a cosine. And the cosines cancel. And remember, I said if you don't remember to take this dx derivative, that this cosine wouldn't actually be on top for us to cancel. It's a good thing that it's up there because it cancels what's on the bottom. But if you had forgotten about it, then you get a 1 over cosine, which is such a harder integral than d theta, which is the integral we actually have to do here. Okay, so let's see, that 3 comes out as a 1/3, cancels with the 3 in the front. Cosines disappear, so this, after all of that substituting, is the integral that we're left with. D theta. And what's the integral of d theta? It's just theta. Stick in our plus c there. And that's basically the answer, except theta was something we invented to help us. This problem had x in it, so the answer had better have x in it. So we just got to figure out what x is equal to, what theta is equal to according to our original substitution. So solving this equation for theta, 2 steps. First, divide both sides by 3. And then take what on both sides? Arc sine or inverse sine. Right, that is theta. And that just gets substituted in for our answer. Yeah, arc sine of x over 3. So that's it. Arc sine. Arc sine, inverse sine are the same. So there's our answer. And if we've got that, again, I'll just pull up our table. What we just looked at was the square root of 9 minus x squared, which looks like number 28 here. How much was a? A was 3, right? Because that a squared was 9. So a was 3, and according to our table, arc sine of x over 3 is the answer. Is that what we got? Yeah. But now we understand 28. We're going to sleep so much better. Like I slept well last night, not worrying about grading your tests, right? You'll sleep as well as I did. All right. So how are you supposed to know to substitute 3 sine of theta as opposed to 3 tangent theta or 3 cosine of theta? It's in the activities, right? So just start the activities. You'll get there after some partial fraction stuff.